Okay, so what did we learn in the previous class? We learned about the branch instruction, right? And then I said that branch instructions are different instruction, right? Why? So, so it is because normal instruction. So actually the arithmetic and then immediate and then memory instructions. The target of each instruction are registers and memory, right? Then I said that usually normal instructions defined by ISA change the data in registers and memory, right? And then branch instruction is different. It is because branch instruction changes the program counter. Okay, so it means that with the branch instructions, we can change the we can change the flow of instructions, right? So if the PC is changed, then we can change the target, the next instructions, right? So I will wait. Yeah? So I think it takes time. Well, okay, I think it's starting, right? 화면이 표시가 안 되는 것 같은데. 예전에. Okay, so I don't know why, but so actually in the previous class we learned about the conditional branch. So conditional branch, the definition of a conditional branch is based on the condition of the branch, then the branch, this branch can jump to the target or the next instruction can be executed. So if the condition is true, then the branch jumps to the target. Okay, so it means that the next instruction, after this branch instruction, the next instructions will be instructions labeled by target, right? And then if the branch condition is false, then very next instruction. So in this example, the next instruction is add I. So next instruction will be executed. That is the definition of a branch instruction. So actually, for the normal instruction, the next PC. So if the current PC is pointing this instruction, the PC is pointing this instruction, and then the PC of the next instruction is the PC plus 4. Okay. Why 4? It is because the size of instruction, the size of RISC-V instruction is 4 bytes. Okay, so I mentioned that PC is the address of instruction, right? But with the branch instructions, so branch instructions can change the PC value. So based on the condition, so this is the BNE. So the equality, not equality is checked. And then if the condition is true, then PC is changed to the PC of the is target. So this is the label of the target program counter. Okay, that is the definition of branch instruction. Okay, and then we learned some various cases of branch instructions from the high-level language code. Okay, and then actually so in this case, so one of the students found that the DC code is not equivalent to the RISC-V assembly code. It's true, so it should be 1. So as you can see, this is the I, this is the I. So I should be 1, and then this is 101. Okay. So as you can see, the 101 is stored in the key 0. Okay. And then also the next line, it should be 1, and then this is 101. Okay. So we need to modify the high level code. Okay. And now in this time, so we will learn about the function code. And then function codes need to be supported by hardware. So in the enough support of these function codes, RISC-V as several instructions, jump instructions actually. So actually the RISC-V supports the unconditional branch. So that is the jump. So we using the jump instruction, we can implement function codes. Then what are function codes? So if we write the code like this, so you can find the two functions. Main function, right? The main function is here. And then you can find the another function named sum. Okay, so this is the C code. And then if the C code is executed, firstly, the main function is code. Okay, so that means that, so I believe everyone practice the left assignment number 1, right? And then in the so if you generate the dump file, you can find the program counter for its main function, right? And then firstly, the program counter is changed to the PC. Okay, actually the first instruction of the main function. Actually, so firstly, the PC is change it to the first instruction in main function. So the main function is call. Okay, and then the instructions in this main function is executed. And then also you can find the other function named sum. So this main function calls sum, right? So, and then the function sum is defined here. Okay, so this is the function code. Okay, so and then you can call you can call the calling function as caller. Okay, so calling function is called caller, right? Caller. Okay, and then actually so called and then called function is called as callee, called callee. Okay, so in this example, the main function calls sum. So in this case, main is a caller, and then sum is a callee. So in English words, so usually the ER is the active form, and then EE is the kind of passive form. So it's similar to the trainer and trainee. If a person get or a person who is trained is a passive form, so it's called trainee. Okay, and then the active form is the trainer. Okay, so so we can understand the caller and then callee like this. So callee is the passive form, it's the called function, and then caller is an active form. So it means the calling function. Okay, so we need to distinguish caller and callee because in a C code, main function is also a function. Okay, so and then inside of this main function, the other functions are called. Okay, so then we need to support this function call. How? So I already mentioned that. So the PC. So when the main function is executed, then actually the PC is changed to the first instruction in this main function. Right? So what does that mean? Sum is called by main function. So which means when the sum function is called, PC is changed. The program counter is changed to the first is the first instruction of sum. Right? So which means the this program jumps to the sum. Okay, so PC is just change it to the first instruction of sum. So that's why in order to support function call, then we need to implement unconditional jump, right? And then how about the end of the function? So you can find the return here. So if the this C statement encounters return, then it is closed here, and then we return to the very next statement of this main function. So this is the return. What does that mean? Obviously, when the return is executed, PC is changed to the very next instruction. So this point, right? This is the meaning of return. So you can think like this. When a function is called, then the PC is changed to the first instruction of callee, okay, the called function. And then if the function completes its execution, then we need to return to the caller. And we need to return to the very next instruction. Very next instruction of the function call. So which means that by changing the program counter unconditionally, then we can implement function calls, right? You understand? So in order to support this function calls, RISC-V has some unconditional jump instructions called JAL and then JALR. So JAL represents the jump and link. So, and then the definition of JAL is, so this is the target of jump, okay? And then if the JAL is executed, then PC is changed to the target, this target, and return address is stored in RA, okay? RA is actually register X1. So why we need to store return address? So it is because when the return is executed, then PC is changed to the very next instruction of this function code, right? So it means that we need to actually this program needs to remember this return point. It is the program counter of the next instruction of function code. Okay, so that's why the return address is stored in X1, and then this is actually RA. So it's called the RA. So it's an ABN name. And then in order to support the return, okay, then this return address, return PC needs to be read from the return address RA, the X1 register. So in order to support this in execution, then RISC-V also supports the JALR. Okay. So what is different? So compared to the JAL, the X0 is the destination register. Okay, this is the destination. Actually, RA is also the destination. And then in the JAL, we use label for the target of jump. But in the JALR, then we can find the 0 plus RA. So what does that mean? Actually, JALR reads address from RA. Okay, this is the return address, and then offset is added, but this is the just return, so offset is just 0. Okay, we just return to the very next point of the jump instruction. So RA plus 0 becomes the new PC. And then the piece we can jump the very next instruction of the JAL. So this is JALR. So this is the jump and link register. And then actually also the very next instruction, the PC of the very next instruction can be stored in the destination register. But in this example, the destination register is X0. And then I mentioned that X0 is the 0 register, which means its value does not change. Okay, it's always 0. So actually, X0 is nothing. So which means that JALR X0 and then 0RA just to represent the return to the return address. Okay, this is JALR. And then we will learn about the pseudo instruction of the RISC-V. Actually, we can use the RET for this JALR X0, 0RA. So you can use just to use and just to use, you simply use HRET. Okay. So this is the just pseudo instruction. It's not real instruction, but you can use this instruction in the RISC-V assembly. So which means that if we use RET, it means return, then it is equivalent to the JALR X0, 0, RA. Okay, this is just return. So this is the pseudo instruction of RISC-V. So which means that actually this instruction does not exist. Okay, but you can use just the fake instruction like RET, and then it is translated into the JALR X0 and 0RA by compiler. Okay, so this is the pseudo instruction. So using the jump and link and then jump and link register, and we can implement function call and then return of the function. So this is the example. So it's a simple function call. So in this example, so we can find the function call here. The simple function is called in the main function, right? And then simple function has only one instruction, which return, right? So let's see the translated RISC-V assembly code. So this is the PC, the program counter of the first instruction of the main function. So as you can see, you can find the label for the main function. Then so the first instruction is the JAL. Okay. So if you see that this JAL instruction, the JAL, RA, and then simple. So this is the target of the job. Okay, the target. So this is the just a function code, right? Because this is unconditional jump. So when this JAL is executed, then the PC is changed to the PC of the first line of this simple function. So this is the labeled by simple. Okay, so labeled by simple. So, and then actually the first instruction, this instruction, and RA. So RA is the destination register of the JAL. And then I mentioned that when the JAL is executed, the next in PC of the next instruction, the program counter of the next instruction is stored in the destination register. So in this case, RA is 1. So this is the program count of the next instruction. The usually PC plus 4. Okay, right? Because as you can see, the gap between this line and this instruction is just 4. It is because the instruction size is 4 bytes, right? So this is the address. So 0x0, 3 or 4 is stored in RA. Okay. And so it jumps to the simple, right? And then the first instruction is just JALR and then 0 and then RA. So it means this instruction reads RA, and then the RA is the 0x3 or 4, and the offset is 0, and then it's a 0. So PC is updated by this value. Then PC becomes the 3 or 4. So which means that this instruction will be executed after this JALR. Do you understand? So this is the return. So I explain how the function is called, then how the return is executed in the function. Okay. So this is the example. So let's see how the function is performed in the real program. So we learned about the caller and the callee. The caller is a calling function. And then, and the parent function. So it is also called a parent function. Okay, it's a parent function. So the caller it encounters a function call, then caller passes argument. So what are arguments? So if you see this example, you can find that main function calls sum, and then these are argument of function sum. Okay, so these are input, or actually the input data for this sum. So these arguments need to be transferred to the sum. Okay, and then when a caller calls a callee, okay, so the caller calls a callee, then caller stores arguments in A0 to A7. So these are registers, right? So arguments are stored in A0 to A7, and then jump instruction, the JAL instruction is executed. Then we can jump to the callee. So callee, when the callee is called, then callee performs the instruction in this function. Okay, and then if you see the simple function of C, you can find the return here, but the return may return result of function, right? So in this case, we use just the void type. So it means that this function will not return any values, but usually we can define function like the int sum a comma b, and then this is example, then it returns the result. Okay, so this return value is stored in the A0. Okay, so this is just the rule. So when the compiler generates the RISC-V instructions for caller or callee, then compiler follows these rules. Okay, so return values are stored in the A0, and then arguments are stored in the A02 from A0 to A7. And then return the point of call, so using the return instruction for JALR X0 0 RA. Okay, the same. And then so these are required processes for function call. And then this is important. Callee must not override registers or memory needed by caller. So I will explain later, but this is very important. So function means that a group of instructions are executed by this callee, okay, callee function. But it means that these are actually in separated group of instructions, which means that a callee is executed, then the data generated by caller needs to be preserved. Okay, if these data are overwritten accidentally, then caller will miss its data, right? So this we need to remember this. So must not override registers or memory. So let's see how the arguments are transferred to the callee, and then how the return values are also stored by callee. Okay. So in this example, you can find the C code here. Then the main function calls if of sums. Then as you can see, the main function transfers 4 arguments to the callee if of sum, and then the result is returned to the main function. So this is the translated RISC-V code. So as you can see, the main function stores arguments. The arguments are 2, 3, 4, 5, and then these arguments are stored in A02, from A0 to A3, and then as you can see, you can find the function code here. It's a jump to the function. So this is the generated instructions of if of sums. Okay, so the instructions are executed at F plus G and H plus I, then results are generated. And then the final result is S3, and then this S3 is stored in A0. So this is the return value. And then it's returned. Okay. So these are examples of arguments, how the arguments are transferred to the callee, and then how the return values are generated and stored by callee. Okay, then actually, so when this main function calls the if of sum, and then actually if of sum execute the several instructions here, right? And then you can observe that these registers are updated by if of sums. Okay, so what's the problem? So main function may store its data to these registers, right? And then these generated values may be used later. But if these registers are updated by if of sums, and then main function may may not use its original data, like stored in the T0, T1, and S3. How can we handle this situation? So what's the problem? Callee also needs to execute instructions, and then obviously, if instructions are executed, then callee will update the values in registers, right? But these registers can be also used by main function, right? Which means that if these data are changed, then the program may generate the incorrect values. So in order to avoid this situation, the possible solution is to store this data to temporary storage space, right? And then this temporary storage space is called a stack. Okay, so in order to avoid this situation, then actually we need to store data in these registers. So these registers are updated by a callee. Then these registers need to be temporarily stored in stack. Okay, so we need to manage this stack when the function is called. Okay, so then what is a stack? So actually we learn, so when the instructions are executed, then the instructions can update the data in registers and memory, right? And then actually we need to avoid the situation that the registers are changed by other callee. Okay, so which means that So registers, in order to store registers temporarily, then these register data needs to be temporarily stored in memory, right? Because there are only two storage spaces, right? Registers and memory, and then we need to keep the data in register. We cannot use registers, right? In this case, because we need to use our registers. So which means that register data should be temporarily stored in memory. So stack is the memory, so memory space. So stack is the memory space. So it is stored in the main memory. So stack is the main memory space used to save data temporarily. Okay, it's a memory space. It's just the memory, right? And then we programs manage this stack space at a fashionable last in, first out queue. So which means that actually we can manage the data in stack using the push and pop operation. So push means that new data is filled in the stack memory. Okay. So and then pop means that the latest. It means the top of the stack. The latest data is removed from the stack. So the push. So there are two operations of the stack memory, push and pop. The push means that new data is filled in the stack, and the stack size is increased because like this. So this is the first. So as you can see, stack includes the data 1, and then new data is added to the stack memory. So this operation is called push. So when the new data is added to the stack, then the memory looks like this. So 1 is here, and then 2 is here. So in this case, 2 is the latest data, right? Filled in the stack. So by repeating push operation, new data is stored in the stack memory like this. Okay. Then when the data is removed from stack, then we can remove the data from the latest data. Okay, this operation is called pop. So in this case, the 6 is the latest data, right? So when this data is removed, so because the stack is the temporal space, then the data stored in the stack needs to be removed. Okay? So when the data is removed, then the data of the latest data is removed first. So it's called the last in, first out queue. Okay, stack works like this. So stack is filled like this. Okay, so it's just the stack, right? And then after that, in order to remove the certain data, the latest data is removed from the stack. Okay, so last in, first out. So you can think like the stack of dishes. Okay, and then when you make the stack of dishes, then you can fill the dishes like this. Okay, and then if we want to remove some dishes from this stack of dishes, then we first remove the top of the stack, right? You understand? So that's why this memory is called stack. Okay, so stack is just the field object. Okay, and then the memory can be also managed like this. So temporary data is stored in the stack space, then stack space is managed like is last in, first out queue. So that's the example. So this is the stack space. Okay, and then I mentioned that the stack space exists in main memory, not register. So it exists in memory. And then also, which means that we can access data stored in stack using the memory address. And then this memory address is called the stack pointer. Okay. So, and then the program is stack is generated, the stack grows down. So which means that the firstly stack pointer is pointing the top of the stack. Okay, top of the stack. And then this is a very large value. Okay. And then if we want increase the stack space, then we just decrease this stack pointer. Okay. So in this example, the stack pointer is pointing address BEFFFAEA. Okay. And then as you can see, this data is stored in the stack. Okay. Stack pointer is pointing here. Okay. And then if we want increase the stack, so which means that we need to add new data to this stack space, right? So we want increase the stack space. So in this case, the stack space decreased. So as you can see, in this example, we need to add two words, okay? So it means the 8 bytes of data, right? Because one word is 4 bytes. Okay. So in this case, this is the new stack point because the stack space is increased. So in this case, the stack we just increase the stack pointer by 8. Okay. And then in this case, SP, the stack pointer becomes the BEFFFAE. Then we can store new data. 2 words, okay? 2 words of data to the stack space. So stack is managed like this. And then so why do we need to run this? Because when the function is executed, and then when the callee executes some instruction, then the data registers need to be preserved. Okay, so it means that these data need to be stored in stack temporarily. So which means when a function is called, we need to increase the stack space, and then we need to store temporary data to this increased stack space. Okay, that's why we need to learn about the stack. Okay, this is a stack space. So let's see the same example. Okay, so in this example, callee if of sum updates the T0, T1 as 3. Okay, so which means that the original data stored in is T0, T1, and S3 need to be preserved. Okay, so which means the data in T0, T1, T3 need to be stored in stack space. Okay, so callee if of sum needs to be modified like this. What is modified? So it's blue letters instructions. So firstly, the stack space is increased because, and then it means that the stack pointer is decreased. And then why -12? So it is because we need to store 3 register data, right? 3 register data S3 and T0 and T1, and then this is the 32-bit. So which means that we need to store 3 words. Okay, so which means we need to increase the stack space for these for storing these 3 words of data. Right? You understand? So stack space is increased by increasing stack pointer. Then S3, T0, and T1 is stored. So you can find the store word instruction. And then what is the address of this store word instruction? So as you can see, stack pointer is the base address. Then we can find the offset here. So in this example, so this is the new stack pointer. So the memory space pointed by new stack pointer, and then T1 data stored here, and then T0 S3 is stored like this. That is the SP plus 4, SP plus 8. Okay. So the data in these registers are stored in the stack space. Then it's okay because the data is stored in the temporal space, and then the registers are updated by instructions of callee. And then return value is generated. Then what is required next? We need to also recover original values to the these registers, right? Because we need to return to the jump point of the caller, which means that we need the callee also needs to return original data to the original registers. And then it's no problem, right? Because the data, we can find data in stack space. So you can find the load word instruction here. Okay. So and then reading the original data from the stack space, then these registers are recovered. Then stack pointer is changed. So you can find that stack pointer is changed to the original value SP. Okay, by adding 12. So when a function is called, this is the callee. When a function is called, the data needs to be preserved, and then this preserved data is temporarily stored in the stack space. That's why we need to manage stack space when a function is called. Okay, it looks like this. So this is the step pointer before a function call. Then during the call. So it means that when a callee is called, the step pointer is change it like this. Then data is stored in the stack. Okay. And after call, then step pointer is restored. Then data is also recovered from stack. That's how stack is working during function calls. But actually, I explained like all registers need to be stored by callee, but there is a register storage rule by RISC-V. So which means that some registers need to be stored by callee. And then some registers need to be stored by caller. Okay, so it is just a rule. Okay, so which means that callee, callee updates these registers. Okay, then the data in these registers need to be stored by callee. Okay. So caller does not need to consider about these registers when a function is called. Function when a caller calls a function. But caller needs to consider these registers before a function call, because the data in these registers are not stored by callee. You understand? So callee just manage the data in these registers. Okay? These registers need to be stored by callee. And then if the data in these registers need to be preserved, then caller needs to store this data in stack before a function call. Okay, this is the assumption. This is a rule for this RISC-V. Okay, so this table shows the which registers need to be stored by caller or callee. Okay, you can find if the table is caller, then if the table is callee, then these registers need to be stored by callee. Then if the table is caller, then these registers need to be stored by caller. Okay. Okay, so actually, so the previous example needs to be fixed. Okay, because in this example, the three registers are updated by callee, but callee needs to store S3 only, because if you see this table, you can find that callee needs to save registers from S0 to S11, but registers T0 to T6 need to be stored by caller. So in this case, the code, this assembly instruction, needs to be fixed like this. So actually, only the callee needs to store S3 only. Okay, so stack pointer is just increased by one, the one word size, and then S3 is only stored in the stack, and then S3 is restored. Okay, because it based on this rule. Okay, then let's see the example of non-leaf function. What is the non-leaf function? So actually a certain function may call other functions, right? So in a tree, this is the tree, okay? And then the last part of a tree is leaf, okay? Right? So it's a trunk, and then branches here, and then as we can observe the leaves on the branch. And then actually the leaves are the last part of a tree. But what is the non-leaf? So which means that this is not a last part. So which means a certain function can call other functions, right? And then this function is called a non-leaf function. Then why do we need to learn about this case? So we can frequently observe non-leaf functions in our program. And why? Why we need to consider these cases? Because we need to manage RA, return address. Why? So think about this. This is the main function. So actually the main function is a non-leaf function. When a main function calls other function like FOO, then RA is stored for the very next line of this function code. And then inside of the function code, the full function, then we can also find the other function code like the foo function. And then which means, oh, this is just the function code, right? The function code. So which means, oh, return address. The function code, good function is called, return address is stored for the next line of the this good function, right? Good function code. What's the matter? What is the problem? Array is updated by this PC, and then same array return address is updated by PC. So which means that this book function calls other function. RA can be overwritten. So we need to avoid this case, right? How? So the problem is, RA is stored here and RA is stored here, and then actually we need to return to this point, right? But if the RA is overwritten by other values, we cannot return to this point. That's the problem, right? Understand? So RA needs to be overwritten at this point. In order to avoid this, we can use stack, right? So we need to avoid overrides. Then in order to avoid overrides, then the original data needs to be stored temporarily in stack. Okay. So non-if function was when a function calls other functions, then RA needs to be also stored in stack. So that's why I just explained the example of non-if function. So this is the example. So when this is non-if function, so stack is increased and then RA is stored in the stack. Okay, and then RA is restored from stack here and then return. Okay, so it means that we can return to the original return point of this function code. Okay, so for the non-if function code, then this non-if function also needs to store return address in stack. You understand? Okay, so this is the example. So F1 is a non-if function and F2 is a if function. So this is the last function. And then F1 will call F2. Okay. So when F1 is called, so we compiler knows that F1 is a non-if function, right? So which means when the stack is increased, stack point as by updating stack pointer, then when the function is called, RA is also stored in stack. Okay, say RA on stack. Then jump to the function 2. Okay, so as you can see, this is the JAL, RA, and then function 2, which means that RA stores the next line, PC of this next line. Okay, so RA is overwritten, but don't worry, RA is already stored in stack. So function 2 is executed and then return from the function 2. And then as you can see, RA is restored from the stack. Okay, do you understand? And then because the RA is restored, then when the return, it's a JALR is executed, then this JALR is this array value, not this array value. Okay, do you understand? Do you understand? Because the array is stored in the stack. Okay, this is the array on stack, and then array is updated. So this is the updated value. Okay, and then array is, so in this point, the array is read from stack Okay, the stack. So this array is this value. You understand? So, and then as you can see, this is the jump JALR return instruction. The return instruction use the RA at this point. So it returns to this parent function. That's how the array is stored in the stack by non-if function. Then how the array will be stored from stack. You can think like this. So in the stack space, array is also stored, and then after function call to function F2, the step point is here. In, the call to F2 and then the call to F2. Then, so you need to remember that array is stored in the stack here. Okay, and then it can be also restored from stack. Okay, this is the function call summary. Okay, so caller, function is called by a caller. Then caller needs to save registers. Okay, and then the argument is need to be stored in the A0 to A7. Okay, and then call function then using this JAL instruction, and then function will be called. Then callee at this point, the callee is called. Okay, callee is called, and then callee execute the instruction, and then callee also needs to save some registers. Okay, at S0 to S11. Then instructions are executed, and then return value is stored in A0. And then these stored registers are restored from stack. Okay, and then return. So when the function is returned from this function call, then caller check the values in A0, that is the return value, then restore any saved registers. That is the processes required for a function call. Okay. Okay. Then let's learn about the recursive function. So what is the recursive function? Like this is the certain function, okay, full function, and then inside of the full function, it calls also its own function. That is the definition of a recursive function. So it means that the same function is recursively, so repeatedly called by itself. So that is the recursive function, and we can also design a function like this. So recursive function is a function that calls itself. Okay. So let's see the example. So this is the example of the recursive function, factorial, right? So this is the fact function, the factorial function, and fact function receives argument n. So the return value is the n factorial, right? And then if you see this factorial function, you can find that, or if n is less than 1, then return 1. And then else, which means that if the n is greater than 1, then return n multiplied by fact n minus 1. So this fact function calls fact function again. Okay. Then how can we translate this recursive function? So So firstly, so how can you design, how can you translate this recursive function? So how can we translate the recursive function to RISC-V assembly instructions, RISC-V assembly code? So firstly, we can treat as if calling another function. So the state is just ignored. Okay. So this is the step one. This is step one. Step one is then this is the instructions inside of the function, and then we can think that that the function can call other function. Okay, not its own function, the other function. You can just translate like this. So this part can be translated like this. Okay. Right? So we just compare the N1. So this is the N. So this is the input argument. The input argument is just compared with the 1. And it's the VGT, so which means that so it's the inverse, the opposite case of the N is less than or equal to 1. So then add I. So we just store, so this is the return. Okay. So this is true case. So for the return case, then we just store 1 to the return value A0, then return. So this code can be translated like this part, right? So we just ignore stack. So that's why before return, we do not consider stack here. So this is the step one. And then else case. So this is the else, right? Else, what is the else? It's multiplied by n is the input argument. So n is multiplied by return value of the other function. The fact itself, so we can think that this is the other function, different function. So actually in order to call fact again, then we need to update the arguments, right? So argument is updated like the A0, so n minus 1, so A0 minus 1. So add I, and then call fact, okay, jump to the fact, right? It calls the fact. And n is here, this is the input argument, the original value. Then actually when the function, after this function call, then this fact function will return value in A0, right? You understand? So then we just performs multiply, like the A0 and then some value, and then store the return value to the A0 and return. Okay. So what's the problem? This is the non-linear function. Okay. So actually we can think that this is the another function, but we do not consider about the stored values. Okay. So each value needs to be stored n argument, because I mark the question mark to the which value. So A0 is the return value from the function, then this A0 needs to be multiplied by P1. But what? I just mark the question mark. It is because n. So n needs to be stored. Okay. So we need to use the n here. N RA return address, because in this example, fact will call other fact. Okay, it said, but return address also needs to be stored temporarily in stack. So actually, n and return address needs to be stored. Okay, so we need to consider stack. Okay, this is the step 2. So we already know that these two data, N and RA, needs to be stored, right? So state is updated by -8, the two data, and then we just store the A0 and return address. And then after that, so also before the return, then stack pointer need to be restored. So this is just update the stack. Then you can find the fact n-1. So fact is also code. And then after that, then we need to restore n because n is used here. So, and then, you know, the n is actually stored in the stack. So n is restored and then stored in the T1. And then we need to also return to the original point. So RA needs to be restored from stack. Okay? And then stack pointer is restored. Multiply and then return. So using these two steps, so actually we can consider this fact n-1 in the other function code. And then if we know that we need to store the n and RA return address, then we can store the n and RA to the stack. Then stack is just restored. This is how the recursive function is translated into assembly code. Okay, it's the same. So we can think that this recursive function code like the other function code, the normal function code. So this is some animation. So this is the animation, but it shows the how the stack is changed by function code. So this is the example of factorial 3. So argument is 3. Okay, so this is the firstly the stack point is increased because the 3, and the 3 is larger than 1. So actually this part is executed. So these are stored in the stack, and then so as you can see, the return address is also stored, and then the n is only 2. Then so it calls fact again. Then fact also store the A0 and return address in stack. So these are stored in the stack. Okay, and then 1 and return address stored in the stack. Stored. And then this stack data are restored from stack. Okay, so stack pointer is restored, and then A0 is read, and then A0 is multiplied by so A0 is multiplied by return value of fact, and then RA is updated, restored again and again. Okay, like this. So I recommend you to follow this line. Okay, this line shows how the stack pointer is changing, how the data is stored in the stack. And then if you can understand how the stack is managed by recursive function, then I believe you can also understand how the recursive function is executed. Okay. Okay, so actually this is the your part. Okay, so I will stop here. Any questions? So thank you for your attention, and then see you in the next class. 감사합니다.